Hi everyone, and welcome to 6,000 Moons on the DK2. So, sit back, relax, and have a little look at this beautiful little game, or demo. Have a little look. Okay, begin! Wow, that's beautiful.
The space above Earth once looked like this. But on October 4th, 1957, something remarkable happened. Carrying only a simple radio transmitter, Sputnik 1, the first man-made satellite, was launched into orbit. And it sent this signal back to Earth. Sputnik was the size of a basketball, but it ushered in a half-century of development and innovation that has transformed our ability to communicate and revolutionized the ways we see and predict the behavior of Earth and space. Since that first historic step, the world has launched over 6,600 satellites. Of those, over 1,200 are still operational. Another 2,600 remain in space, either in orbit or as debris. What you're viewing isn't an artist's rendering. It's an orbital simulation. It combines a computational model for orbital mechanics with publicly available data on the size and orbital parameters of the world's active satellites and the known low-orbit debris. There's a strong connection between the job each satellite does and the orbit in which it's deployed. We can look at some of these roles and orbits more closely. Here, we've used color to highlight four major classes of orbits and roles. Nearest the Earth, below about 2,000 kilometers, are the low Earth orbit satellites in green. Tight circular orbits are ideal for imaging and remote sensing and allow for strong signals with the lowest delay. LEO satellites are deployed for sophisticated reconnaissance, magnetic sensing, forest fire and river flow recognition, mapping, biological experiments, and many other uses. Further above the Earth, in orbits that are noticeably non-circular, are the satellites in highly elliptical orbit, shown in red. HEOs are often deployed for very specialized work in astrophysics, or for communications tasks that demand a particular synchronization with regions of the Earth. The medium Earth orbit class, shown in gold, is home to a range of crucial navigation, scientific, and communications craft, including the major GPS systems. Orbital periods for MEOs range from 2 to 24 hours and are generally less eccentric or more circular than the red HEO bodies. At the outer edge of the MEO range, in a blue band sometimes called the Clark Belt, are the GEOs, geostationary equatorial orbits, along with other members of its parent class of geosynchronous orbits. We'll attach our point of view to one of these satellites and look more closely at their characteristics. If you have a game controller, this is something you can do freely later in this simulation.
Okay, attached to a satellite. The one that carries YouTube. Where's it? Wow.
A geosynchronous orbit is designed to match the Earth's own rotation period of one sidereal day. If you look at the Earth from our current position, attached to a geosynchronous satellite called Thuraya 3, you'll see we're holding to a position centered somewhere on the Indian subcontinent. A geostationary Earth orbit, or GEO, is a very specific geosynchronous orbit. It not only matches Earth's rotational period, it maintains a near constant position relative to a very specific stationary point on the surface. If you look at this band of satellites, though, you'll notice that not all are precisely tracking to the equatorial plane. Some are in orbits that are tilted or inclined. We can zoom in and isolate a few different GEOs and examine why this is.
Okay, let's examine why this is.
When satellites orbit the Earth, the satellite orbit forms a plane that passes through the center of gravity, or geocenter, of the Earth. An equatorial orbit is flat. Its geocentric plane cuts through the Earth's equator. An inclined orbit is tilted relative to the equatorial plane. That tilt angle is called the angle of inclination. Here we've isolated 3 active geostationary satellites that have differing angles of inclination. The blue INSAT 3A is in a classic geostationary orbit. Its orbit has been established to consistently dwell over India, and its transponders communicate with stations within that region. The green Taraya 3 satellite has an inclination of about 4.5 degrees. This slight tilt away from the equatorial plane gives it a broader ground track area. The Tharaya's transponders cover an area that includes India, Central Asia, and Australia as a result. And the gold NASA TDRS has an even greater inclination of about 14.3 degrees. The inclination and positioning of TDRS-7 is driven by its role as a communications relay. We've looked at orbits that are more or less equatorial. Let's look at 3 types of orbits that are quite different.
Skip.
A polar orbit has an inclination around 90 degrees to the equator. Here we've isolated the set of low Earth polar satellites with nearly circular orbits. This pattern, particularly in LEO range, is useful for applications that require full, regular coverage of the Earth and its poles. Mapping, global reconnaissance, and weather, and other Earth science observations have been revolutionized by these types of satellites.
It's a lamb.
So what do you do if you need the continuous ground tracking of a GEO, but over a polar region? This is one application of highly elliptical orbits. Here, we've attached to the satellite called Integral. Integral is an astronomical satellite for observing the gamma-ray sky. Since it's collecting data from space, not the Earth's surface, its ground track matters a bit less to its mission than the time it spends at highest altitude, or apogee. Another characteristic is the variation in velocity. As an HEO object approaches its perigee, where it's closest to Earth, it speeds up. The Integral has a perigee of about 2,300 kilometers, and it completes one transit around the Earth every 2.8 days. Sometimes, the mission of a satellite is to collect data in the visible or infrared range of the spectrum. To do so, its orbit must maximize its time over the sun-covered portions of the planet. These LEO imaging and sensing satellites are deployed in coordinated networks of sun-synchronous orbits, which repeat their ground tracks at regular intervals and can be synchronized to provide overlaps in coverage. Here, we see a simple example of this in the Belgian QB50P1 and P2 satellite pair. Note how this small satellite pair, orbiting in sun-synchronous coordination, is designed to maximize telemetry from the sunny side of the Earth. You may also notice that these satellites have an inclination slightly greater than 90 degrees. This causes them to orbit slightly in opposition to the Earth's natural rotation. This pattern, called retrograde orbit, is a requirement for maximizing synchronicity with the illuminated portion of the planet. It can be more expensive to deploy large satellites in retrograde because it requires more fuel to launch into opposition to the Earth's natural spin. So the tiny 1 kilogram size of satellites like this Belgian pair is a conscious design choice.
Wow, whoa.
Before we leave the low Earth range, it's worth noting that not all man-made orbiting constellations are so benign or carefully orchestrated. Some can only be described as chaotic. What you see here is the simulated orbital activity of approximately 2,600 pieces of debris that were once the Fengyun 1C weather satellite. In January of 2007, In what was later confirmed to be a self-directed test of anti-satellite technology, the People's Republic of China struck this satellite with a rocket. The debris trail first streamed along an orbital path dictated by the satellite's own orbital momentum. But over time, it has steadily spread, and this simulation is based on Celestrak data from late autumn in 2014.
Wow, sit back again. Wow, that's nuts.
Our last stop in the tour will be back in the medium Earth orbital range for a look at one of the most famous and transformational satellite networks in operation. At about 20,200 kilometers is the Global Positioning System.
Hey!
There are 3 operational networks for GPS, but perhaps the most well-known is the United States Navstar system, shown here. GPS satellites are deployed into one of 6 orbits, highlighted here by expanding the Navstar F-series. These orbits are arranged in planes with inclinations at approximately 55 degrees to the equatorial plane. Each GPS satellite travels at approximately 14,000 kilometers per hour and circuits the Earth every 12 hours. And they are, in many ways, the best example of the ways in which mankind's mastery of orbital mechanics and satellite communication has transformed daily life on the planet below. This ends the 6,000 Moons demonstration. For more information on the computational model and data behind the experience, please visit us at binsoftware.com. You can now continue to explore the simulation using the following keys. Thank you for your interest in 6,000 Moons.
Thank you. That was very good and educational. Oh wow! So I can like move in. Wow, that's crazy. I can move left and right. Can I? Going retrograde around the Earth. Oh. Yes, well this video is probably long enough. while I muck around. Then you can actually pick out satellite names. Wow. Yeah, so thank you very much for watching. Whoa. From wherever you're watching from. Here. Or here. Turn that light out. Wow. I'm a satellite. I'm a human satellite. Beautiful. Thank you very much for watching. Catch you next time. See ya. Peace and shit. Hey.